so this is going to be very simple because I thought it was going to be mainly for students, and or it is, okay, then whatever. So expert people can happily sleep or prove some theorem, which is very good for mathematics. All right, now, what is the issue? So as you know, if you have a dynamical system, let's say X is some manifold and F is some smooth diffeomorphism, then you can, or maybe you have the continuous version, you have a flow on some manifold, then you can, one fundamental thing you can look at is Birkhoff averages. Or the time is continuous. Okay, so everybody knows that there is Birkhoff theorem, so you can take the limit for the limit, this limit for exists if you have, of course, you must have some invariant measure, then it exists almost surely, and with respect to any invariant measure, and so you can call the limit f plus, sorry, phi plus. And this is an invariant function, and if the system is ergodic, then it will be, if the system is ergodic, it will be equal to the average, mu almost sure. Now, of course, the issue is that normally dynamical systems have a lot of invariant measure, so it means that in principle this function f plus is rather complicated. There will be some point, not many, but some point in which there is no limit whatsoever, and in other point it will be equal to the average with respect to some ergodic measure. But there is an interesting case, which is the case in which you have a uniquely ergodic system, then there is only one invariant measure, and then if there is only one invariant measure, then you know that the limit must be the average with respect to this invariant measure. Okay. And once you know this, it is very natural to ask what happens to the deviation from the ergodic limit, right? Because in many applications, you don't really have the limit, right? You just are interested maybe in a sum with a very large n, but not infinity, and then you would like, okay, you know that what is the limit, but the question is, I mean, how far are you from the limit? And that means that you want to, for example, consider this quantity. Okay, so you know that this will converge mu almost surely to 0, but the question is how fast. Okay. Now, if you have let me be very, very loose, what is called the chaotic system, something strongly chaotic, then essentially if you have decay correlation for the measure mu that are fast enough, then it is known that there is the central limit theorem. So it means that this quantity is more or less of order 1 over square root of t. So this gives you some, or if you want, if you take the ergodic integral, then this is of order square root of t. Okay. So that is the situation that you have for systems that have very strong chaotic properties. But the question that I would like to talk about today is the other extreme, a situation in which instead you don't have very strong chaotic properties, and parabolic systems are a typical example. So let me just, in order to see what happened, discuss really the simplest possible example. The simple possible example is a rigid translation of it on a torus. So you have the torus T2, and on the torus T2 you have the differential equation x dot equal omega. Okay? And so the solution will be phi x equal x plus omega t mod 1. Okay? So this is the torus mod 1. So this is okay. So that is a simple ODE to solve. Everybody can solve it. This is the solution. So that, what does it mean? It means that you have the torus, you have the flow lines, something like that, whatever, and just you move at constant speed along these flow lines. Very well. And now you would like to, now this one, of course, it depends from omega, right? I am interested in the case in which omega 1 over omega 2 is not in the rational. So this is irrational flow on the torus, then this is known to be uniquely ergodic. The only invariant measure is Lebesgue. Okay? So it means that if you take a function that is, now I want to study this thing for in this particular case. So I take a function that is zero average with respect to Lebesgue. So mu is Lebesgue. I take phi such that as zero average. This clearly has zero average, so I'm considering this case. And I want to study the integral from 0 up to t, phi composed phi s x ds, and see how does it grow. Okay. Now it turns out that it is convenient to, instead of attacking directly this problem, which one could do, but it is much more convenient to study the co-boundary equation, which means that I want to study this. I want to see if there is a function g such that if I take the derivative of the function in the flow direction, then I get phi. So in particular, this means that if I take the derivative with respect to time of g composed phi s at x, this derivative, it is just exactly this, because the vector field of phi is omega. So it is exactly equal to omega g composed phi s of x. And if this is true, then this is going to be phi composed phi s. So it means that phi is just a time derivative of something. And then if this is the case, you can put this in here, and then you, instead of writing this, you write that. You write this, and of course this is just g composed phi at time t minus g, t x minus gx. Okay. So in this case, if there exists a function g, let's say a bounded function g, such that that equation is satisfied, then the answer to the question, what is the growth of this ergodic integral, is it doesn't grow, because this is just bounded by twice the sup of g. So And that is very different from the situation we were looking here, in which instead you have a growth of order square root of t. So it's kind of completely different behavior of the ergodic averages in this particular case. But of course, the question is, does it exist a solution of this equation? Okay, so then if you want to look at this problem, the simplest way to do it is to just compute in Fourier transform. So you take the Fourier transform of this guy, and what do you get? You get I omega c times g hat c equal phi hat c, where g hat is the Fourier transform of g, and phi hat is the Fourier transform of phi, and xi belongs to Z2. Okay? So now you want to solve this equation. All right? Of course, you may be in trouble because if xi is 0, then this is 0, this better be 0. But it is 0 because I assume that the integral of phi is 0. So we know this, you can write this is the same as saying phi hat 0 is equal 0. Okay, for xi equals 0 is satisfied, and for xi different from 0, then you can at least write formally the solution. Since I assume that the ratio between omega 1 and omega 2 is not a rational number, this, and since this means that this is never 0, of course, because if that is 0, it would mean that the ratio is rational. And so at least, I mean, formally, this makes some sense. Okay. The question is, does this define a reasonable function? Remember that I'm looking for a function that is bounded. All right? So of course I have to say, I mean, already this I have to justify. Let me just, let's just say that I take this C infinity just not to bother. I mean, you can take CR for some R that makes some sense, but I mean, okay, no, let me be, I'm lazy, but I don't want to look too lazy, so let me just take it like that. I take it in the Sobolev space HP. So that means that the P is a natural number, and this means that the first P weak derivative of phi are in L2. That's what it means. Okay. All right? But I will consider the case in which, no way, that's what I want to consider. All right, so since at least the worst possible case is P equals 0, well, yeah, I don't know. This depends upon if in N you have 0 or not. This is a question that I could never decide. So people have different idea about that. I don't know if 0 is a natural number or not, whatever. I don't think so, but maybe people think otherwise. In any case, even if it's 0, that would be L2, so there is in L2 is perfectly okay to write this thing. And the question now is the usual problem of small denominator, because this, okay, is not 0, but it could be extremely small. And let me just take some very special situation in which omega 1 over omega 2 or omega 2 over omega 1, doesn't matter. I mean, it's just a matter equal alpha is a quadratic irrational. One could consider much more general situation, but I mean, like a Diophantine, but I mean, let me just consider this case, which is the real simple situation. Okay, so if this is a quadratic irrational, then there is a general estimate, which is the following. Then exists gamma bigger than 0, such that this is bigger than gamma C, where C is the square root 1 plus C squared. That is actually true for quadratic irrational, if I am not mistaken. Okay? So that means that this, okay, can be small, but not that small. And now this means that you can have an estimate on how big these coefficients are. These are smaller than phi xi time c divided by gamma. But this guy is in HP, so it means that I can compute the sum for xi in Z2 of C P minus 1, I guess, G hat C 2 square. So if I apply this estimate, I get gamma minus 2, sum for xi in Z2, and then I get C 2p minus 1, and then I get c squared minus 2, so I get that, and then I get phi hat c square, but this is exactly the HP norm, so this is gamma minus 2 phi HP. So that means that G is in HP minus 1. So that means that you can solve the in this particular case, you can solve this cohomological equation over here. And you get an information of the regularity of G. You just lose one derivative, essentially. All right? So what? Well, now you have the Sobolev embedding theorem that tells you if P is bigger than 2, then G belongs to L infinity. And if I recall correctly, or maybe 3, something like that. I mean, there is some theorem like that. And this means that provided phi is at least in H2, then you get that this ergodic average does not grow. So there is one obstruction. Either it grows, of course, if you take a function, either, and this is like saying that the integral from 0 to t phi compose phi s is more or less mu phi t. So either it grows like t, or it doesn't grow at all. That is the result of this, the analysis of this extremely simple example. And that is kind of the situation in much more complicated example, much more complex example. For example, systems that have been studied are systems like the Horocicle flow, or area preserving flows on surfaces. So this is Forni, Flaminio, this is Forni. They got the sharpest result. But there are a lot of people that have worked on this stuff, including some people in the audience. And the Teichmuller flow also, but I don't want to talk about all that. I want just to tell you two things about this more general situation, that in the more general situation, it appears a phenomenon that is slightly different. There are intermediate possibilities. So for example, for the Horocicle flow, it happens that this ergodic integral can either grow like t, or there is a countable set of powers, and it can grow like such powers. So you can get this that grows, where did I write it? Here. It grows like t, or it could grow like t to the alpha for certain alphas. Okay? But there's nothing to do with this behavior here, in which it grows like square root of t, and it is a random variable, essentially, if you rescale it by square root of t. This is just a growth of a completely different type. And, yeah? No. For the Horocicle flow, there is no central limit theorem. For the geodesic flow, there is central limit theorem in negative curvature. Geodesic flow has exponential mixing if in negative curvature, and that is enough, more than enough to get the central limit theorem. But the Horocicle flow is uniquely ergodic, and it does not have central limit theorem. It has this property instead, that the decay, the growth of the ergodic average grow with certain powers. I mean, and there are obstructions. If the function is a generic function, then it will grow like t. If the average with respect to the Liouville measure is 0, or the Riemannian measure is 0, then it will grow like t to some power smaller than 1. And then there are certain distributions. And if you are in the kernel of this distribution, then you grow with smaller power until you essentially are constant, and then you are a coboundary. That is the picture. Okay? But the proof of all these cases, somewhat, are based on some very explicit computation. In principle, very similar to what I did here. The idea is that you use, for example, the analogues of Fourier transform, like representation theory, and using that, you are able to compute, all right? So, for example, if instead of, for example, you have an Horocicle flow not on a manifold, this is Horocicle flow, but a manifold is constant curvature. Okay. So if you, for example, are on a Horocicle flow on a manifold of strictly negative curvature, but not constant, then it is not really clear how to play the game in the same way. So there are few results about more general situation. For example, there are results by Musa, Marmi, and Marmi, Musa, and Yokoth on interval exchange map of a little bit not necessarily linear, which interval exchange map, for people that know, are related to polygonal billiard. So that is kind of a situation in which you have a flow that is not necessarily linear. Or there are some results by Buffetov, also a little bit more general, but they are kind of partial results in which you cannot recover all the general theories that people are able to do in these cases. So I wanted to see if there is a way of reproducing such, a different approach that doesn't use like the equivalent of Fourier transform. And so I tried some very simple example. So this is work in collaboration with Ginlietti. He was a postdoc of mine. And the idea is the following. So you can look at this system. So this, there is some foliation, which is the foliation along which the flow moves. And you can think that this foliation, if this ratio is a quadratic and rational, then you can see this foliation as the stable manifold of an Anosov map. So what is an Anosov map? An Anosov map, a linear Anosov map in this case. So a linear Anosov map would be something like this. where SA is a matrix, and the element are, let's make it easy. Let's say that the elements are natural numbers, and the determinant of A is 1. Then you can compute the eigenvalue, since the determinant is 1, then and then let's say that the trace. Yeah, well, let's say that the trace is bigger than 2. Bigger. Yeah. So then you can check that the eigenvalue are 1. It has 2 eigenvalues, lambda and lambda minus 1, and lambda is strictly bigger than 1. So if you consider this situation, you can choose the IJ in such a way that the stable manifold is exactly this, made of this line on which you have the flow. So you can see this flow as a flow along the stable manifold of an Hausdorff map. And this is very similar to this situation over there, to the Horocicle flow. Because in the Horocicle flow, what is the Horocicle flow? It's a flow along the stable manifold of the geodesic flow. Okay, so you have a map, a flow that is hyperbolic, all right, it's geodesic flow. It has a stable and unstable manifold. The stable manifold are the Horocycles, and you move along the Horocycle with some unit speed. And that is exactly the same idea. Instead of having the geodesic flow, I have an Hausdorff map. The Hausdorff map has the stable manifold, and I move along the stable manifold with unit speed. And I get exactly this example. Okay. Very well. And now I want to, let me just, when do I have to stop? I lost track of my time.
13 minutes.
13 minutes, okay, so then I have to hurry up. Okay, so let me just then revisit these computations that I did with this point of view. Okay, so I want to compute this quantity. I want to compute this quantity, then I do the following. I consider this an Hausdorff map F, and I introduce F minus 1, compose F, compose phi s of x ds. And now what happens? It happens that if I have phi, what is this? Well, it means that I have a point x, I have some piece of stable manifold, and I apply the map F. So this will go on the point Fx, and this will also be a piece of stable manifold, but it will be much shorter. If this is of length t, this will of length s, this will be of length lambda minus 1s. That is what it does. So it means that this, or if you want to write it, this means that this is equal to phi lambda minus 1s compose fx. You start from the point fx, and then you have a piece of stable manifold, and that is what people call, in this case, renormalization. Essentially, this equation is a super simple instance of renormalization, what people in the business would call periodic renormalization in this case. And then if you apply this, then you get the integral from 0 to t, phi compose f minus 1, and then compose lambda minus 1 s, compose f of x, ds, okay? And now you change variable, and you get the integral from 0 to t to lambda minus 1 t, phi compose phi minus 1, sorry, f minus 1, and then you get compose phi s compose f of x, and then you get lambda, and then you get yes. So you see, it is very tempting to introduce an operator, which is in the jargon is called the transfer operator. And this transfer operator is defined like that. L of phi of x is equal to phi compose f minus 1 of x times lambda. And then this, you can write it, the integral from 0 to lambda minus 1 t of L phi comp phi f of x ds. Okay, so this is a computation that seems a little bit stupid, but there is something that you can do. You can do the same computation a little bit more in general. Instead of composing with f, you compose with fn. And then it's just an easy exercise to see that this is just equal. So if you can just compute and you find that this is minus n x lambda n. And so this is n. So you see, and this is n, sorry. So you see, you want to know how big is this integral. You do this game, and you get that you get a new integral in which you have a different function. You don't have phi, you have ln phi is another function. This function you integrate again along the stable manifold, I mean along the flow, but for a much shorter time, and you start from a different point. So what? So essentially this guy is essentially an ergodic integral of, like this one, only is the ergodic integral of a different function, ln phi, sorry. Okay, so it means that if you know how this grows, then you are done. What you need to know is what is the growth of this. Just choose n such that lambda minus n t is more or less 1. And then you are integrating on a line of fixed length. It could be between 1 and 2, something like that. And so the growth cannot come from the integral because the integral is on some interval of fixed length. The growth can only come from this operator. So, and then you have to look at this operator. And if you look at this operator, it turns out that the operator has the following spectrum. It has the spectrum in lambda, of course, and then that's it. And then there is 0. And that's all the spectrums. This is sigma of L. So what does this mean? This means, sorry, what am I talking about? No. And then there is something that depends on the regularity on which you are looking at this problem, okay? So this is, if phi is in HP, this is some nu that depend on P. Okay? And this is essential spectrum. That is the picture. And if you take P large enough, you get this is smaller than 1. And what does this mean? It means that this guy essentially cannot grow, because if this is the maximal eigenvalue, is associated to an eigenvector. The eigenvector is simply the Lebesgue measure. So it means that L has a spectral decomposition of the type I don't know, Q plus, and then there is 1 time the integral. So P of phi. And this guy here, it has, does not grow because the spectral radius is smaller or equal than 1, and this one is just the integral with respect to back. So if this is 0 average, this is 0. And so you recover the fact that the integral does not grow. So that there are some subtlety because, there are some subtlety because you have to specify exactly which function, what is the space of function on which this operator acts, and this is a little bit complicated. I don't want to enter too much on that, but that's more or less the idea. Okay, so this is a different point of view. I have obtained the same result, more or less, in a more complicated way. Right? Before it was just Fourier transform. Now I have some operator. I have to discover what is the right functional space on which to look at this, transfer operator, and then I have to study the spectrum of this transfer operator. So it looks like I have essentially made a job that is the job of the Office for Complication of Simple Things, because it's just. But it just happens that this is more flexible, this point of view, because now consider the situation in which A is not linear, but is just an Anosov map. If it is an Anosov map, then you can copy this. The only difference is that this is not going to be just multiplied by lambda. It will be some tau that depends on n, on s. It's just how much a stable manifold gets stretched if you apply f time the Anosov map. But still it will be stretched exponentially fast. And so then this one, instead of being, so this will be just tau n of t, this will be some Jacobian, okay? And then the transfer operator will have some Jacobian. Okay, this is just the derivative. The Jacobian is just the derivative of this guy with respect to n, which is just the stretching that you have. It's just the integral of the contraction along the stable manifold. And that's it. You just get exactly the same formula. Sorry, this is going to be now. You have just to, this is just tau n of t, as before. And now you have just to choose this in such a way that tau n of t is of order 1. So you just apply, you have some very, very long stretch of stable manifold. You apply the Anosov map. You keep applying it until this stable manifold shrinks and becomes more or less of length 1. Then you stop. And there you have exactly the situation in which you have again, the integral of a curve more or less of length 1 of this function here instead of this function here. And it is along the flow, but starting from a different point. So again, the growth of this integral just depends on the growth of this transfer operator, and then the problem is reduced to analyzing the spectrum of this transfer operator. And again, in this particular case, you can show that if f is, I think I'm done, if f is smooth enough, you can show that the picture is still like that. So either there is an invariant measure, unique invariant measure, which is the Margulis measure for the Anosov map, turned out to be the invariant measure for the flow. And if the function has 0 average with respect to this measure, then it is a coboundary in this particular case. So the result is not so exciting, but the technique is kind of general, and in principle it is reasonable that it can be applied, for example, to a Horocicle flow of non-constant curvature. And there are some preliminary results in this direction by Adam, who is a student of Baladi, or it has been applied to pseudo-nodes of situations, so to this situation by Gusel recently. There are some applications by Butterly and Simonelli on the case of Heisenberg-Near flows. So in principle, I mean, that is just an example that we did in order to show that the situation this approach can work, but the hope is that it can be applied to much more general situation, and this is work in progress, and so with this I stop. Thanks a lot.